in case there are any questions on any of the topics which you want to ask for the quiz, feel free to do that. So any questions on Qs or BSTs or AVL? By the way, Salman pointed out that in last time's mock quiz, in the last example, AVL problem, the answer given by me was wrong. I think I had mentioned it as 4, but I think there are total 6 rotations required, 2 single rotations and 2 double rotations. I'm sure some of you must have found it out. Just check that once. I have updated the answer on Moodle. Thanks, Salman. But just check if I have made any further mistake.
Sir,
Yeah, Vishnu, go ahead.
did you record yesterday's discussion?
No, we did not record yesterday's discussion as such. The questions were rather simple. So we just had the quiz for half an hour and then discussion for 20 minutes on those questions. So we didn't record it. Yeah. Any other concerns, questions? All right, so let's continue our discussion. Whatever we are discussing today is not there for the quiz, but it will be there for the quiz 3 or Ensign. Okay, so Murari says questions are not visible to us. Oh, is it? I see. Okay, let me maybe I'll just do that right away so that I don't forget in setting up your questions. Okay, mock quiz. Edit settings, review options. To the okay, can somebody just quickly check if the quiz is open now for you to see the questions?
So it is open. So those who have given the mock quiz, it is open for them.
Oh, I see, I see. Oh, that is the problem. Oh, I see. Oh, I see. Okay, I understand what's happening. Okay. I think I'll have to change the timing probably. Okay, I have updated the end time to 12th October, so hopefully the mock quiz will now be visible to all of you. Okay. Yeah, can somebody who has not attempted the mock quiz? Okay, great. Thanks. Thanks, Murari. All right, so we'll continue our discussion on this. Are there any other questions? Okay, sir, some of us are getting 6 for the last question. Can you solve it? Yes. So as Anish mentioned. So I think I just declared that the last question, AVL, it should have the answer as 6 rather than 4, because there are 2 double rotations and 2 single rotations. So that is correct. Salman had pointed it out to me. So I have updated the, yeah, no problem, Anish, that's okay. So I have updated the answer on Moodle. Okay. Any other concerns? Okay. So we know that BSTs provide, I mean, both BSTs and AVLs provide order height search. In case of BSTs, that order height could be order log n, whereas in AVLs it is order log n. Sorry, BSTs it is order n. And we also know that AVLs are too strict about height balancing. As soon as there is height difference of 1, we have to worry about height balancing. So that, I mean, although we know that rotations are constant time operations, doing that almost every alternate insertion and deletion, that becomes expensive in practice as far as absolute time is concerned. Right? So the expectation there was, can we construct some sort of lightweight mechanism which need not maintain height balancing strictly, in the sense that it doesn't maintain it on every alternate insertion or every time the height balancing property needs to be maintained, but overall we still get some sort of order log n complexity of insertion and removal. So with that, there are multiple trees that got created. B trees, for example, where you store multiple values inside a node, which are used in databases. But then in the context of memory, I mean RAM, we could also use something called as Splay Trees, which also get used, by the way, in some of the backends of the data structures. Right? And then there are something called as red-black trees, which actually get used in the context of some STLs. So let's discuss specifically about Splay trees. We are not going to look at RB trees, I mean red-black trees and B trees, but we will look at Splay trees a little bit, at least at the theoretical level. We might not implement those, but we'll definitely look at how rotations can be useful in the context of devising a new mechanism. So Splay trees do provide order log n search, but that doesn't mean that individual insertion and deletion can be done in log n time. Right? So what they provide is some sort of log n bound in the amortized sense. Right? So we briefly discussed amortization some time back, but I think the best way to understand amortization is probably a real world example is your data packs, right, in your mobiles. You have this some data packs which have 1.5 GB limit per day or 2 GB limit per day and so on. Right? That means that per day you can guarantee that the amount of data that you use will not go beyond, let's say, that 1.5 GB. But then there are data packs which have which provide, let's say, 25 GB for, let's say, next 7 days or 15 days, and then there is no daily limit. Right? So per day you can actually use more than 1.5 GB. In fact, you can use as much as 25 GB per day. But there is a guarantee that within those 7 or 15 days, you will not cross that 15 GB limit or 25 GB limit. This is amortization, where there is no bound on individual, I mean, there is a large bound on the individual operations, but combined operations have a different bound. So for example, in this case, individual insertion or deletion might actually take order n time. Individual insertion or deletion might actually take order n time, but it is guaranteed that over m such operations, your bound will not go beyond m log n. If across m operations, that is m inserts and deletes, if your total time complexity is m times log n, then on an average, you get log n bound per insertion and deletion, although the worst case time, right? So average time and worst case time are different. Average time is log n, which is m log n upon m, whereas individual operation in the worst case might actually take more than log n, right? So this is how the amortization works, and this is a real bound. I mean, there is no problem with this bound as such. Of course, log n is tighter, and if you have individual operation as log n, definitely m operations are going to take m log n. But by giving some more time to certain operations, we are guaranteeing that some other operations will definitely take lower time. So there is a zero sum game here, right? So your total bound is m log n, and therefore if somebody has to gain in time, somebody has to lose in time. This is similar to our Huffman coding example, where we said that everybody can be log n number of bits. If, however, somebody wants to reduce the number of bits required for frequent characters, then some other character needs to increase the number of bits beyond log n, right? So this is exactly similar to that. Any questions on this high-level idea of amortization? Vishnu says, can you repeat the meaning of expensive in practice? Expensive in practice essentially means that the constants are large. So when we say that some operation is log n, order log n, that means that the complexity function is going to be c times log n, c1 times log n plus c2, right? So that is what we have seen when we were discussing complexity. This c1 and c2 turns out to be large, and these are dependent on how you implement, what is the underlying data structure you use, what is the hardware on which you run this, etc. And it turns out that although the constant time operation happens for rotations, that's what we have proved, but these constants turned out to be large because we have to perform these operations very often, right? So as you can see, we just inserted probably 8 or 9 nodes in that AVL example in the mock quiz, and we had to do 4 rotations, out of which 2 are double rotations. So these are like every alternate insertion or deletion is going to result in rotation. Rotations are in general costly. I mean, although it is constant time, but you are manipulating pointers. Pointer dereferences might not be available in the cache, or it might not even be available in memory. You have to do some page loading in RAM, or cache miss might occur in the cache, etc., compared to what happens in the context of arrays, for example. In such cases, the overall absolute time increases, although the theoretical complexity remains the same. So that is what we would like to attack by providing a little lightweight mechanism which is not so strict about maintenance of height. Aniruddha says, is amortized same as average complexity? No. Amortized means that over m operations you are providing a guarantee on an average per operation, right? So average complexity of an operation might turn out to be different. For example, we say that quick sort, which we have not yet studied, the sorting algorithms we have to study. Quick sort is on an average n log n time, where n is the size of the array. But the worst case complexity is n squared, right? So average essentially means that you take random instances, right? And then on that you find out how much time it requires, right? So, and then you try to plot it and give bound, not plot it, but you give a bound based on the randomization of the input. Whereas in amortized case, it is m log n worst case complexity. It is a guarantee. In case of average complexity, there is no guarantee that in the worst case you will reach m log n or n log n in the context of quicksort. Whereas in this case, you can guarantee that in the worst case, after m operations, you will require m log n bound, right? So therefore, amortization gives a better bound, a better guarantee compared to an average complexity. Murari says, is it like defining time complexity? Like, is it only true for m greater than some integer? Yes, so m needs to be a relatively larger number, that is correct. So I think, okay, I'm not able to recall exactly what is the what are the constraints on m. I think I'll have to find that out. for the amortization case, but yes, M needs to be sufficiently large. That is correct. But I'll confirm this once. Any other concerns? Okay, so let's understand how that is going to be done. At a very high level, splaying is related to widening of the road at junctions to improve visibility, right? So you are going by a small lane, but you want more visibility at certain place as soon as you reach a junction. So the visibility of access nodes needs to be improved. What does that mean in the context of complexity? It essentially means that whatever nodes you are accessing, those you should be able to find quicker for the next access. Right? Many times the kind of operations that we use on the data structures, or in general whenever we search for certain values, it turns out that some small number of values get searched more number of times. Some small number of values get searched more number of times, and a large number of values get searched for a very small number of times. Right? So the number of times, for example, your Angelina Jolie will get searched for, Googled for, is probably going to be much larger than let's say IIT faculty member, right? So that's what is the difference in which we typically say 90-10 heuristic or 80-10 heuristic. I mean, people say that it is a rule, but it's actually a heuristic, which does not have any real theoretical basis. It's just that that is how the data is. That is what we derive from the data. So some nodes in this AVL or in this binary search tree are going to get accessed most often, whereas there will be a large number of nodes which will be accessed very few times. And that becomes, those scenarios turn out to be very useful for Splay trees, and that is what we are going to essentially do. So let's understand that in the context of Splay trees. And yeah, most importantly, the BST need not be height balanced, which essentially means that Splay trees are also examples of BST. So we maintain the BST property of in order sorted nature. Okay, so as I was mentioning, the worst case search complexity is still bounded by order n. And that means that you may say that worst case searching over m operations is m log n, right? But that doesn't happen, and we'll see how that doesn't happen. Sorry, mn, not m log n, mn. And if we have to maintain this property that over m operations, the bound should not be mn, then we have to make sure that the worst case no longer exists. So initially, let's say I'm searching for some leaf node, right? So the worst case is going to happen for the leaf node, because I'm going to search for that element all the way from root to the leaf. Let's say the deepest leaf is the one that I plan to search. So there is, you are designing a search mechanism for the Splay trees, and I am your advisory, not advisory, I am your adversary. Adversary meaning I am some sort of opponent. I want to make your life difficult. That is what faculty members do, right? So I want to make your life difficult. So what I will do is I will tell you what to search for. You design the algorithm, right? So you are designing the algorithm for search. I will tell you which element to search. So now if you give, I will create a tree BST that both of us agree on. And then the deepest node, I'm going to tell you, okay, go search for that node. So you will go all the way down. And since this is not an AVL, you will probably end up taking order n time for that element. Next time I'll say, okay, search for the same element. And I'll keep repeating this. And if that happens, your complexity over m operations is going to be mn. Now, if you have to make sure that adversary, which means me, is not able to achieve this mn bound, then you have to make sure that the worst case which was originally existing no longer remains. That does mean that if I am searching for that node again, then the bound should not come as order n, right? I should take much smaller time compared to order n, which I required for the first one. This is similar to caching, where we say that if I search for an element for the first time, maybe it is not in the cache, I'll incur a penalty. I go all the way to the RAM and then fetch that data from RAM to the cache. But if I access that element again, with a good chance that element is going to be present again in the cache, and therefore I reduce the overall time complexity. That time complexity, overall time. In this case, I'll say that if the element is searched first time, I will incur order n time, but if I search it again, I should be able to do it very fast, and very fast meaning probably close to order 1. That is going to be the advantage of Splay Trees. So let's understand how that needs to be done. But that means that the worst case, the element that I searched for or accessed, that cannot remain as the leaf node, or that cannot remain at the bottom of wherever it was in the tree. So what Splay Trees do is that we move the searched element all the way to the root. We move the searched element all the way to the root, so that next time you access it, it is going to be close by, nearer the root, right? Because you might not access the same element again and again repeatedly. Let's say I'm searching for 5, 3, 5, 2, 5, 9, something else, and then again 5 and so on. So 5 will be nearer to the root. If that is guaranteed, then there is a possibility that as an adversary, I'll not be able to create a sequence to give you the worst case order n per element, right? So that is what happens. The second aspect which becomes important in this case is that the height of the tree needs to also get reduced. If it was n time for the first search, not only that the element should move up, but over operations, the height of the tree should also not remain order n, because otherwise I'll always find somebody else which has order n height, and therefore I'll keep on getting order n time for m operations. It becomes order mn. So the height of the tree should also reduce. So these were the two important points. The accessed element should move upwards. It should not remain at that place. The second one is the height, which was probably larger, that should also get reduced. So with these two high level thoughts, let's understand what Splay Trees do. But any high level questions at this stage? Okay, so let's concretize this further, right? So yeah, a deep node cannot retain its position after the access. Otherwise, your faculty member will come up with a sequence which requires order mn time. So the element needs to be pushed to the root, right? So in this case, I'm pushing to the root, but that need not always be the case. Like you can push it closer to the root so that the access time reduces to probably a constant rather than, or even within log n. That might also be all right. So just that in this case, we are going to push it to the root because in real life, that's what happens. And this requires us a series of rotations, and we know that the rotations have the capability of reducing the height. So we might be able to reduce the height of some part of the tree. And whenever an adversary tries to access something which is very deep, we might end up doing rotations such that we will reduce the height much by a greater possibility, right? So if the adversary is playing the worst case, we might do some more operation. If the adversary chooses an element which is closer to the root, then we will not do much work, right? So that is the high level picture. There are two important points here. One, we might require more than constant number of rotations because we are moving that element all the way to the root. Due to rotations, we might require actually order of height number of rotations. Thankfully, the rotation is order 1. So we might require order of height number of operations, unlike we had for the case of insertion in the context of AVL. The second thing is, if you recall, I mean, in general, the way we think about a search on a data structure, it is a read-only operation. In general, when we think about search or find in a data structure, it's a read-only operation. But now, search on Splay Trees is no longer a read-only operation because we are modifying the data structure. Right? This is a very different aspect that you will see in this particular case, and this thought that a particular find might not be a read-only operation. It actually changes the data structure. This might turn out to be a very important from the perspective of maintaining the overall complexity of different operations. Right? In fact, since we are on this discussion, I'll also mention that in C++, some such operations are typically marked as const. Right? At the end of the function, we typically mark it as const, which indicates that this function does not change anything with respect to the overall backend data structure, nothing in the object. Right? But then if you have this such functions which are essentially read-only, but they are also modifying something. For example, like I'm maintaining, you have a linked list and I'm searching for an element in the linked list. And what I want to do is that whenever I search for an element, I want to move that at the start of the list. Alternatively, I might want to just do some profiling where I want to increment a counter for every node inside. So originally the operation was read-only. Now because of this profiling or by moving the elements, it has become a non-read-only operation. So how does the world know about it? Actually, the world does not need to know about it. The world need not know how the organization of that data is, right? That is our API interface. This profiling or reordering of the nodes, this is internal to the data structure. So what C++ says is that you can still mark the function as const, but then whatever you are planning to do, that you mark with a different keyword. Does anybody know what that keyword is in C++? Whenever you are making changes inside a const function. Yeah, this this keyword doesn't exist in C. It's called as mutable. Right? So the keyword mutable essentially means that the function is a const, but internally you are still modifying something, right? So that is allowed in the context of such examples, some such search in Splay Trees or reorganization of data when you find an element in a linked list, etc., or do some profiling, etc. Right? So those of you who are interested, you can look up about mutable. All right, so let's come back to this. So we might require a series of rotations, and some other nodes might also change their heights, and which results in some height balancing. Right? So let's understand this with a specific example. Right? So I want to search for K1, and what I do end up doing is that K1 is somewhere deep in the tree. Maybe a leaf node, may not be. But what I do in this process is that along the path, whenever I am searching for K1, I am going to move this K1 up. Right? Whatever we know about rotations, that can help us move this K1 up. Right? So what are the rotations that we require? Can somebody tell me to move K1 up? The question is, what are the rotations required with whatever we know of to move K1 all the way to the root, such that the BST property is maintained? No? Okay, Aniruddha says L, R, 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 R. Okay, Nikhil says L, R, R, R. Okay. Any other suggestions? Okay, Surya Narayanan says L, R, R, R. Okay. Okay, Aniruddha has corrected his suggestion. Okay, yeah. So we require 3 R's following 1 L. Right? So as you move 1 L, then K2 goes down, K1 goes up, and then now the path becomes K5, K4, K3, K1, K2. Right? And then you require 3 more rotations such that K1 reaches the root. Right? So precisely that's what gets done in the context of Splay Trees. And as you can see, if you might require the order height number of operations to do that. So we do 1 L and then 3 R's, and we get a tree like this. Right? As you can see that the K1 has moved up, that is true, But then some of the other nodes have also moved up. What are those? Whatever we tried to, so for example, K2 has moved up. As far as K3, K4, K5 are concerned, those have come down. So this is where the zero sum game comes into picture. Gain for somebody is loss for somebody else. So gain for K1, K2 results in loss for K3, K4, K5. Why? Because maybe those are the ones which are not going to get accessed again and again. But note that they have not moved too much below. For example, K5 was the root. Now K1 got access, and therefore K5 has moved just one level below. If next time K5 gets accessed, K5 will again come back to the root, and the traversal that is required for K5, the number of rotations will not be high. So if K1, K5 keep getting accessed often, even if you use an alternating sequence, they will be nearer to the root. And that is going to be an advantage, and that seems to be very good from the perspective of real life examples. If some node like K3 doesn't get accessed at all for a long time, it will remain below, and that is good. So the overall height in this case has actually reduced. If you see the last tree, the overall height seems to have reduced for C and D, right? And that is beneficial in general. So there is some small height balancing that has happened as part of these changes, as part of these rotations. And if you keep doing this, hopefully the tree will continue to remain almost height balanced. We never said that the height balancing needs to be maintained at every node or at the root and so on. That we are not saying at all. We are just saying move this node all the way to the up. That's it. Right? And in the process, this is getting done. And then the analysis magic makes sure that we provide the m log n bound on the height over m operations. Okay, so let's summarize that part. Right, so what did this move achieve? Next, access to K1 is fast. For K2 also it is fast, whereas for K3, K4, K5 it has become slower, and overall tree height has reduced. Right? So if we play adversarial, that is your faculty member is now at play, I am deciding what element to search. Right? So what I will do is that construct a very, very left skewed BST. Right? That is the worst case. And I create the insertion order n to 1 so that n becomes the root, n minus 1 is its left child, n minus 2 is grand left child, and so on. 1 becomes the leaf. And then I am going to search for 1. And that pushes 1 all the way to the root. Correct? So it has to follow n minus 1 links. Then I search for 2 because 2 is now at the leaf node. That needs to move n minus 2 links all the way to the root, and then 3 and then 4, right? So what is the complexity that I get in terms of this? Any suggestions? And I can actually repeat this process, right? So first time I require n minus 1 traversals, next time I require n minus 2 traversals, then n minus 3 and so on. And I can repeat this process. And when I push n back to the root, 1 has come back to the leaf node, and I can repeat this process. So then isn't the complexity going to be n minus 1 plus n minus 2 plus n minus 3 all the way up to 1, and then repeat this process over m operations. So the complexity of 1, so this is going to be m times n, right? So is it m times? Yeah, overall complexity over m operations, or in this case n operations, is going to be n square, and therefore for order of n square, and therefore for a single traversal the complexity will still be order n. Then we have not achieved anything. This is like searching in a BST. There is no advantage, right? So any thoughts? That's right. So Aniruddha says that after the first access of 1, it's no longer really left skewed, because you are not performing only moving that 1 all the way to the root, you are also moving some other parts upwards, right? So that is what happened with K2, for example. and therefore we can't use this analogy for the adversarial traversal. This we can use for BST. This we can use for BST, but this we cannot use for splay trees, right? So that is what is the BST part. Whereas in case of splaying, it doesn't turn out to be that way. So let's formalize it in the context of splaying. This process is called as splaying when we perform order height rotations and move the element up, right? So for that, like we did K1, K2 in the context of AVL, we are going to do with X, Y, Z in the context of splaying. For that, we require 3 nodes, X, Y, and Z, which are going to be in some sense parent, child, and grandchild, right? So this is what is going to be there. So let's say that X is a non-root operation, right? X is a non-root element. If it is a root element, then we don't do any splaying because it is already at the root. If X as parent is the root, rotate X and the root. So we require X and Y in this case. Otherwise, X has a parent P and a grandparent G, right? So I'm not using X, Y, Z. I'm using X, parent P, and the grandparent G. All right. So this is what we will do. If it is X and the parent, then we know how to take care of that. You just rotate it so that the parent and the child relationship gets exchanged, and that becomes an order 1 operation. Okay. And once again, using these, there are going to be 4 cases similar to our insertion case, and we can transform each of these cases as I'll show visually. So let's say that this is going to be left-right case, where it is the left child's right subtree, where grandparent, parent, and X are going to be present, and that I'm going to perform some sort of, okay, so this is the left case, and similarly 2 more cases are going to occur, right? So this was our left-right and then the left case. In case of the first one, left-right case, we are going to do some rotation, which we call as, or not me, but the literature calls as zigzag operation, because we are alternating, whereas the second one is called as zig-zig, right? So what we will do is essentially same as what we know. We are going to do a left rotate here so that P goes down and X becomes its parent, and then we perform a right rotation so that G and P become the children of X, right? And then we have the remaining elements as shown in the figure. So this is our essentially the left rotate followed by the right rotate. In case of zigzag, essentially we are going to do right rotate, and that is going to make X as the root of this subtree, and then P becomes its child, and G becomes its grandchild, right? So the total exchange or total reversal of the roles for GPX becomes XPG. And then the 2 other cases are going to be exactly the mirror images of this, right? So, and those also we know how to take care of that. And more importantly, this needs to be repeated. So X might have a parent, right? So I mean, for example, G might have a grandparent. So that also needs to be taken care of, because X needs to move all the way up, right? So that is what is required. So you might have to repeat this zigzag and zigzag, and we know that zigzag and zigzag are going to be order 1 operations, because we know single and double rotations are going to be essentially order 1 operations. So that is what yeah, so this is essentially LL. Okay, so let's do that on a particular example which we had earlier. So we are going to do a zigzag, and that becomes essentially what we had done earlier. So K1 becomes the root of the subtree rooted at K3, and the rest of the upper part remains the same. The down part ABCD remain the same, but their parents keep changing. And then we apply the same procedure for K1, K4, K5. Right? So that becomes K1 moves up as the root, and then K4, K5 exchange their position. So K5, K4, K1 now get reversed as K1, K4, K5. So that becomes the other. So again, zigzag and zigzag are order 1 operations, and you might have to do order height operations to reach the root. Okay, so coming back to this complexity part where we said that it's going to be in the worst case order of n square for the BST. Let's see what happens in the context of a Splay tree, at least with an example. We might not be able to do it with the actual complexity, theoretical complexity, but let's say I do a find one. Right? So Aniruddha said that it doesn't remain left skewed as such. So let's see what happens in this case. But before that, there is a question by Saicharan. Given searching is going to be a more commonly performed operation, isn't it more costly to perform so many rotations for each rotation? Wouldn't it be better to perform rotations during insertions itself, like in the case of AVL? That's a very good point. So the point that Saicharan is mentioning in the context of real world applications is that insertions are much smaller compared to the searches, right? So many times we perform reading, right? So for example, the number of times people might be checking their, let's say, balance in an ATM might be more compared to the number of times they take out the money, right? Or add the money to their account. So, or in general, the number of students that get added to a batch is just one-time operation, whereas operations on, okay, how many students exist, what are their CGPAs, what are their hostels, etc. All of these operations happen much larger number of times. So typically these are called as also OLAP operations, right? So online analytical processing. So where the searches or finds are much larger in number compared to inserts, and deletions are typically very rare. I mean, much smaller compared to even inserts. In that case, isn't it better that if the insertions are really rare, why don't we optimize the search? Right? That is, let's spend more time in the AVL where we are spending enough time, but that is more or less static. That is one time almost, that insertions happen at once. Then after that, most of those are search. So the complexity is going to remain as order log n. We don't need to even get into the rotations at all if we are using AVLs. That's a very good point. And if the application is such, yes, you should be using AVL in such cases. You might actually end up using V trees for such cases. But yes, that is going to be a better operation. The many of these data structures that we are studying, right, as part of this course, these are useful when you have actually transformations happening on the data. If actually there are very few transformations happening, you might end up using even an array to store this information in a sorted manner, because anyway the insertions are rare. So even if I have to move the elements in an array, big deal, it's going to be very rare. In that case, I might actually be using maybe array access, so I don't have to worry about pointers. I can use log n search in the array, etc. And that might turn out to be better. Or I can use a hash table, which might turn out to be a better data structure even compared to an array if most of my elements are static in nature. Right? So yes, that is a valid point. But many of these linked lists, stack, queues, all the tree-based data structures that we are studying, as well as the hash tables, then the heaps, etc. All of these are going to, or graphs, these are all going to be useful when you have arbitrary transformations to the structure of the data structure, which means that I'm going to do insertions and deletions. But of course, you are going to have arbitrary, I mean, you should look at how the access pattern is, and depending upon that, you should decide the data structure. That is correct. Saicharan says, what is the motivation of Splay trees if AVLs are better? Again, this better is a subjective term depending upon the application. Right? So if you're in case of AVL, the kind of insertions and deletions, if those are happening more frequently, right? So, or not more frequently, but happening many number of times, and AVLs are, the absolute time of AVL is actually going to become larger. Right? Splaying is not maintaining this property at all, right? The height balancing property. Yes, there are rotations required. But if many of the searches are happening, well, searches are not going to be really a problem for AVL. But think about it this way, that in case of AVL, if an element moves to the leaf node, right, so it is always going to require log n time. Whereas if I am performing a search for an element more number of times, that initial search will probably be order n. but the other searches are always going to be order 1 or nearby order 1. And that is going to be a big advantage in the context of search. But in case of inserts and deletes, I might not even maintain that property in the context of splay trees of height balancing. So I don't do any rotations if I'm accessing, let's say, if I'm inserting a particular node. That is also. So there are definitely positives and negatives of both the sides. I'm not saying that splay trees are the best data structures. Yes, you will be able to find out a use case for AVL also, like you are mentioning. But you will be able to find a use case for splaying also, where the second onward searches might turn out to be order 1, whereas in case of AVLs, it will continue to remain order log n for if the element is at the leaf or nearer the leaf. Saicharan says, why are we moving the element to the root? I feel it's better to move up by one level instead. So if you move it only by one level, you will be able to construct this omega of n square complexity. You have to move it all the way such that you get within the bound of log n. So you will have to move it much upwards, right? And log n is much smaller compared to n. Right? Otherwise, we will keep getting. If you just move upwards, the complexity will still remain order n to order n minus 1, and then we will get this omega of n square.
Sir?
Yeah, Saicharan. Yeah, go ahead, Saicharan.
Am I audible?
Yeah, you are audible.
Yes, sir. So what I was thinking is, if one is a very rarely searched element, taking it to the root makes no sense, right? So
Yes.
if we construct it like, moving it up by one level, the more frequently called ones will, over time come up to the top, and the less frequently called ones will remain at the bottom. Now, when we take everything to the root, what happens is like even if it's being searched very rarely, we are bringing it up all the way to the top, which is not required.
You are right. So what Saicharan is suggesting is that let the movement to the root happen in steps, as if the element gets accessed more number of times, it is anyway going to move to the root. But if an element is not accessed often, maybe it's accessed very rarely, but it does get accessed, then there is no point in really moving it all the way to the up. That is correct from a real world perspective, and you might want to design such a data structure, that is okay, but you will not be able to give this complexity, amortized complexity bound if we do that. Plus, splaying is not a randomized or let's say I am not able to in case of splaying, I am able to give the guarantee that across m operations, you are not going to require m log n time for search, which we will not be able to guarantee, amortized guarantee, if we use any different mechanism, not any different, but this particular mechanism, where we are moving just by a constant number of steps upwards, right? And to argue in that manner, I can always say that, yes, we might be moving it all the way to the root, but assuming that that is rare, that means that there are other elements which are actually getting accessed more often. They will not really move too much down. They will move probably 1 or 2 levels below if they are actually getting accessed more often. So it is still okay if this element moves up. In the overall scheme of things, this will actually move much down. Maybe if it is occurring towards the end of the sequence, then maybe it will reach near the root. But if there are other elements which are rare, which have been accessed early on in the sequence, those will actually move much below. Aniruddha says, in playing adversarial, in the repeat step, if we give different accesses, will the overall complexity still be order n? Yes. So in the case of splaying, this has been proved that in the context. So I'll have to check about what that m is. I mean, are we saying it for? I mean, we cannot say it for arbitrary m, because m can be 1, and then there we have seen that it is going to be order n. So I'll have to check what that m is. But yes, as far as m is larger, and I'll have to check how the distribution of searches are, then the overall complexity is still turning out to be order n not n, but order m log n. Basu says, won't it be costly to move an element to the root every time a new element is searched? Can we define a limit, like if the element is at less than 5 nodes away from it, we don't move it? Yes, these variants are possible, and I don't know if in the real world actually Splaying uses any of such things, but yes, these are possible, and these are going to definitely improve the absolute running time of the Splaying. But as far as the complexity is concerned, that will remain the same. You are right that in practice you can use these heuristics to improve the absolute running time. That is correct. Aniruddha says, if you are talking about distribution, isn't it average case then? Yes, you are right. I'll have to check that. So I'll have to check that. I'll check that, Aniruddha, and get back. What is this meaning of M? I'll get back on that. Yeah, and that is not the case, which means that it should be, even if you have a worst case distribution, right? Even if all the elements are turning out to be all uniformly distributed, that might turn out to be the worst case, right? That even in that case, right? So when I'm talking about distribution, I'm talking about the worst case possible distribution. Even in that case, if we are able to guarantee m log n amortized complexity, then we can say that it is going to be order log n amortized average complexity per search. All right, so I think we'll have to stop here, but and all the best with your quiz. It is at 3 o'clock on Saturday, that is tomorrow, and on Moodle. I haven't yet prepared the paper, so let me do that now. Yeah, but if there are any questions, feel free to mail me or post it on the Google group. We'll be able to discuss. No problem. All right. I'll wait for any further questions. Otherwise, the class is over. Again, yeah. So is it 90 minutes? Likely to be 90 minutes. But I mean, I'll be able to post that after I have created the quiz. Murari says, I'm getting a feeling even if the tree is highly skewed after M operations, there will be enough height balance to get order edge operation adversary. Yes, that is what happens essentially, that the height gets reduced, and therefore that complexity does, that height does play a role in the complexity derivation for the amortization, but I have not yet looked at that carefully. So I'll have to look at that and give you the answer. Sure, that is correct, Murari.
Quiz is at 3 o'clock, you say?
I think so. That's what I posted, I think, on the group. I think the quiz is at 3 o'clock. Yes. Because there was a suggestion from you guys that morning you have some other engagement, and therefore we decided that it will be in the afternoon. Nobody complained about that, so we decided that it will be at 3 o'clock. Yeah, please check my email carefully. I think I have posted it on the Google group. Any other concerns? Okay, so if there are no concerns, then we'll stop here. See you.